Welcome to my talk. Today I'll tell you about counting and sampling perfect matchings, and this is joint work with Farzam and Shayan. Let's start with some notation. In this talk, all graphs will be unweighted and undirected, and all graphs will have an even number of vertices. Let's define M of I to be the set of matchings containing exactly I edges. And let's define little m of I to be the cardinality of M of I. Notice that when I is equal to n, we are talking about the perfect matchings. For example, consider this graph. It has exactly two perfect matchings, so little m of n is equal to 2. The main algorithmic task we will consider is that of computing the number of perfect matchings. Valiant famously showed that it's sharply hard to compute this quantity exactly, even if the graph is bipartite. A natural question is, can we approximately compute it? One of the most fruitful techniques to solve approximate counting problems has been this equivalence between approximate counting and approximate sampling, which was shown by Theorem, Valiant, and Vazirani. In particular, for matchings, this result shows that the existence of an efficient randomized algorithm to approximate the number of perfect matchings is equivalent to the existence of an approximate sampling algorithm from the uniform distribution over the set of perfect matchings. In this direction, Gharan and Sinclair gave Markov chain-based approximate sampling algorithms that are efficient if the ratio of the number of n-1 matchings to the number of perfect matchings is small. Notice that this does not include the class of all bipartite graphs, but for example it does include the class of all dense graphs, where the degree of every vertex is at least half the number of vertices. Gharan, Sinclair, and Vigoda gave efficient Markov chain-based approximate sampling algorithms if G is bipartite. A major open problem in the field of approximate counting and sampling is whether we can do the same for every graph, not just bipartite graphs. In our work, we show that there exist efficient algorithms for these tasks in the important special cases that the graph is a regular expander. Before stating the result, let me define an expander. Let's suppose that G is a deregular graph, and let A tilde be the normalized adjacency matrix of G. Clearly, the eigenvalues of A tilde must lie between -1 and 1, with the largest eigenvalue being exactly equal to 1. We'll say that the graph G is an epsilon spectral expander if every other eigenvalue has magnitude at most epsilon. For example, Friedman showed that almost all deregular graphs are epsilon spectral expanders, with epsilon being around 2 over square root d. Now let me tell you our first result, which is algorithmic. Let's say G is a deregular epsilon spectral expander. Then there is an n to the O of log d or log 1 over epsilon time randomized algorithm for approximate sampling and approximate counting perfect matchings. Let me make some remarks about this theorem. Firstly, if epsilon is smaller than an inverse polynomial in D, or if D is a constant, then the running time of this algorithm is polynomial. Secondly, by Friedman's theorem, this gives a polynomial time algorithm for almost every deregular graph. Thirdly, the results also hold if G is approximately regular, which means all of its degrees are in theta of D. And fourthly, our theorem requires that epsilon, which is the spectral expansion, is smaller than a fixed constant, and this is only achievable if D is larger than a fixed constant, which is an important caveat of our theorem. Next, let's switch gears and talk about a very different type of result. The van der Waals conjecture was a theorem proved by Falikman and Igorichev, which states that if G is a deregular bipartite graph, then the number of perfect matchings is at least d over e to the n. For reference, a trivial upper bound one can prove on the number of perfect matchings is d to the n. A natural question is whether we can prove similar types of results for classes of non-bipartite graphs. This inspired the Lowash-Plummer conjecture from '86, which conjectures that if G is a deregular d-1 edge-connected graph, then the number of perfect matchings in G is at least some constant based on d times some other constant based on d to the n, where these constants are positive such that C prime of D goes to infinity as D goes to infinity. Recall that a graph is D minus 1 edge connected if its min cut is at least D minus 1. Ideally, for a strong version of this conjecture, we would want C prime D to be at least some polynomial in D, or optimally we would want C prime D to be D over E. So far, the Lowash-Flower conjecture is still open. The best partial result we have is one by Esprit and others, who show that we can get C prime D to be a constant which is slightly larger than 1. Notice that C prime D doesn't vary with D in this result. The work of Bolobash and McKay shows similar results for random D-regular graphs. In particular, their work implies that the number of perfect matchings in a random D-regular graph is essentially at least D over E to the n, with probability 1 minus inverse polynomial in D. Notably, this only holds if D is small enough compared to n. Now let me state our second theorem. We show that if G is a D-regular epsilon spectral expander, then the number of perfect matchings in G is at least D over E to the n times this error term. This error term can be shown to be negligible compared to the first term if epsilon is small enough. If one views expansion as a strengthening of edge connectivity, then our result can be seen as a partial resolution of the Lowash-Flower conjecture, in the special case that G is an expander. Next, take D to be a random D-regular graph. Friedman's theorem implies that with probability 1 minus inverse polynomial in n, epsilon is smaller than an inverse polynomial in D, which means that with the same probability, the error term in the above theorem is negligible. Therefore, with high probability in random D-regular graphs, the number of perfect matchings is essentially at least D over E to the n. This can be seen as an improvement over Bolobash and McKay's result, whose work only implies any bound on little m of n with high probability with respect to D, whereas our result implies a bound on little m of n with high probability with respect to n. Next, I will give an overview of how we prove our two results. For the rest of this talk, let G be a D-regular epsilon spectral expander on 2n vertices. Our main technical lemma is the following. Let k be an integer, then the ratio of the number of k matchings to the number of k plus 1 matchings is upper bounded by this quantity on the right. To get some intuition about the right hand side of this inequality, let's plug in some different values of k. If we start with k equals n minus 1, then the lemma says that the ratio of the n minus 1 matchings to the number of perfect matchings is at most n to the O of log D over log 1 over epsilon. You might recall that this is the same as the running time of our algorithm from Theorem 1. On the other hand, if we plug in k to be slightly smaller at 1 minus epsilon times n, then the main lemma shows that the ratio of k matchings to k plus 1 matchings is at most a polynomial in D. Notice how rapidly the upper bound has improved from k being close to n to k being close to n times 1 minus epsilon. This lemma can be used to show both our theorems. Let's start with how it implies the first theorem, which is the algorithmic one. Recall this result of Gharan and Sinclair, who showed that we can count or sample perfect matchings approximately in time polynomial in n and the ratio of the number of n minus 1 matchings to the number of perfect matchings. As in the previous slide, let's apply our main lemma with k set to n minus 1. This implies that the ratio above is at most n to the O of log D over log of 1 over epsilon, which directly implies that their algorithm runs in the required time. Next, let me say why the main lemma implies theorem 2, which is the lower bound on the number of perfect matchings. The first step in our argument is to show a strong lower bound on the number of matchings of size 1 minus epsilon times n. The reason such a bound can be true is because the expander mixing lemma shows that for any matching of size at most 1 minus epsilon times n, there must be an unmatched vertex with a substantial fraction of its neighbors being still unmatched. The second step in our argument is to show a lower bound on the ratio m of n to m of 1 minus epsilon times n. This can be shown by multiplying the main lemma for all k between 1 minus epsilon times n and n. To complete the proof of the theorem, we can simply multiply the inequalities in step 1 and step 2. Notice that most of the error in the theorem comes from step 2. It remains to argue why this main technical lemma is true. For simplicity, let's assume k is equal to n minus 1. So the main lemma turns into the following statement. By some arguments from the literature, like those in Gharan and Sinclair's paper, it suffices to prove the lemma at the bottom, which says that for any matching of size n minus 1, there exists an augmenting path of length that's bounded by log base 1 over epsilon of n. Recall that an augmenting path for m is any alternating path for m which begins and ends at an unmatched vertex. Take this example. If this is a matching m, then here is an augmenting path for this matching. For the rest of this talk, we will show how to prove this lemma, which says that any matching of size n minus 1 has a short augmenting path. We'll use a result from Tanner, which says that if G is an epsilon spectral expander, then it's essentially a 1 over epsilon vertex expander. Let me start by making the additional assumption that G is bipartite. Then it turns out the lemma has a pretty simple argument through alternating BFS. Let me tell you what I mean by that. So let's consider the following bipartite graph and a matching M of size n minus 1. Our goal is to show that there exists a short augmenting path in this graph. That is, there exists a short alternating path from S to T in this graph. Let's construct a sequence of subsets of the bottom partition of this graph, starting with B1, which is the neighborhood of S. Next, let's look at the set of the matched neighbors of B1. Next, let's look at the neighborhood of this set, which we can call B2. We are going to repeat this operation until our set Bi contains the vertex T. It's not too hard to convince yourself that since the graph is a 1 over epsilon vertex expander, the size of Bi is increasing with every iteration, and that the number of iterations before Bi contains every vertex in the bottom partition is at most log n base 1 over epsilon. Next, it's easy to see that Bi, by definition of Bi, is exactly equal to the set of vertices reachable from S by an alternating walk of length at most I. And since the graph is bipartite, we can shortcut all these alternating walks, and we get that Bi is equal to the set of vertices reachable by an alternating path of length at most I. Since T is in Bi for I being approximately log base 1 over epsilon n, this shows that there is an alternating path from S to T of length at most log base 1 over epsilon n. This completes the proof of the lemma in the bipartite case. What if G is not bipartite? Can we adapt the argument from before to work in this case? This turns out to be a very difficult task. And one of the ways to see this is to see that alternating walks cannot be shortcut to alternating paths in non-bipartite graphs. For example, this is a non-bipartite graph, and it does have an alternating walk from S to T, but it's easy to see that this graph has no alternating path from S to T. This was one of the crucial steps of the proof in the bipartite case, and it seems hard to get around this in the non-bipartite case. So it seems that we need a new idea. The main idea of our proof is the following. Instead of trying to run the bipartite analysis on the non-bipartite graph G, let's take a random bipartite subgraph of G and try to run the analysis on this subgraph. If we get that with non-zero probability, this bipartite subgraph has a short augmenting path, this would imply that the original graph also has a short augmenting path. Let me tell you how we construct our random bipartite subgraph. For example, take this graph G, where the orange edges are the matching M. Let's orient each edge in the matching arbitrarily. These orientations are signified by the arrowheads on the edges. Now let me say how the bipartition is created. I'm going to separate the two halves of the bipartition by this blue line. First, let's arbitrarily place the unmatched vertices, one on each side of the bipartition. Next, for each matching edge, pick a random direction, either left or right. If the direction is left, then assign the two endpoints of the matching edge to opposite bipartitions, such that the arrowhead faces the left. And if the random direction is right, then do the same, but making sure that the arrowhead faces the right instead. Once we do this for all the matching edges, we have obtained a bipartition of the graph. Let omega be the set of n-1 random coins we flip to get to this bipartition. And let g of omega be the bipartite graph you get after deleting all edges that go from one partition to itself. Notice that g of omega still completely contains the matching m, because for each matching edge, we placed its endpoints in opposite partitions. Since g of omega is always a subgraph of g, it suffices to show that the lemma is true with probability more than 0 over the randomness omega. Here is why we might expect the lemma to be true for g of omega with non-zero probability. We know that g is a vertex expander from Tanner's result, and the following argument shows that g of omega is a slightly worse vertex expander in expectation. Here's what I mean by that. Consider a set S and G. We know that since G is a good vertex expander, the neighborhood of S is large. Now consider a random bipartition of G, and for simplicity, assume that S is all on the left of this bipartition. After deleting all the interpartition edges, we see that about half of the vertices, which were originally neighbors of S, but outside of S, still remain neighbors of S. Notice that g of omega is not likely to be a good vertex expander for all sets, but at least for individual sets, we are able to show that they are likely to expand. This raises the question of whether all the sets that we encountered during the approximately log n iterations of alternating BFS are likely to expand simultaneously. Perhaps we can take a union bound over all these sets. Unfortunately, this turns out to not provide a strong enough bound, so we need to do a more careful analysis. This ends up being a bit tricky because there are dependencies between whether different sets expand, and our main technical contribution is how to account for these dependencies. Using this, we are able to show that the lemma holds with non-zero probability over the omegas, completing the proof of the lemma. I will conclude with some future directions. Firstly, recall that our two results made use of the fact that epsilon, the spectral expansion, was close to 0. One natural question is whether similar results are possible with weaker expansion. For example, if epsilon is closer to 1, or perhaps using only one-sided expansion. Along these lines, we conjecture that similar results are possible using conductance instead of spectral expansion. Another question is whether we can utilize this idea of random bipartitions in a stronger way. In particular, maybe we can reduce the problem of counting number of perfect matchings in general graphs to counting the number of perfect matchings in a random bipartition. The latter task is something we are able to do efficiently due to the algorithm of Gharan, Sinclair, and Vigoda. So it might be conceivable to estimate the average number of perfect matchings across random bipartitions, perhaps using a Markov chain over bipartitions, and then using this to compute an estimate of the number of perfect matchings. Finally, the Lowash-Plummer conjecture on d-regular d-1 edge-connected graphs is still open. A solution to this conjecture might also lead to insights that give approximation algorithms for the number of perfect matchings in these graphs, which are not currently known. This is the end of the talk, and thank you for your time.